Today I'm going to introduce to you a very interesting piece of technology which is actually part of vanilla kernel called USB over IP, and also I will show how to exploit it. So first of all, a little bit about myself. My name is Ignat. I work for Cloudflare. I'm a systems engineer there. My primary interests are security and crypto. I also like to work on low-level things like Linux kernel, different firmware, and BIOS and other stuff. I'm more builder than a breaker, so I'm not professional InfoSec person, but you may ask why am I presenting a vulnerability. So I usually try to stay alert. If I want to use some kind of a system or a framework, I do try to check if it's open source, that the sanity of its implementation. So our plan for today is I will briefly describe to you what USB over IP is. We will then go over how it's implemented in Linux. Also, I will briefly show you how to export a USB device over IP network. Then we will jump into vulnerable USB IP code in the Linux kernel. We will discuss potential exploit impact, and lastly, if you do want to use this technology, I will give you some tips how to make your USB IP setup secure. But first, since it's a vulnerability disclosure, you're probably all wondering, like, am I vulnerable? So let's check. How many of you have previously heard about USB IP? No one? That's good. So probably you all are safe. So the general rule of thumb is that if you never heard of the USB over IP and you never used it, you're safe. If you do use USB IP but didn't patch your kernel from last year, did patch your kernel from last year, you're reasonably safe. And if you didn't patch your Linux kernel from last year, so probably you have bigger problems, so I cannot help you, sorry. So what is USB IP? So USB IP basically, it does what it sounds it should do. So it's a framework which allows you to share devices over the network. It's implemented in driver or device agnostic way. It's not implemented for a particular types of USB devices, so it works on the lower level and it can support almost any USB device. So it does that by sending URBs over plain TCP connection. So URB stands for USB request block. It's a basic building block of the USB protocol. It's the lowest message which is used by all USB devices and USB hosts to transmit and receive data. And this framework is implemented for Linux and Windows. So we will particularly focus on Linux implementation today because it's interesting from vulnerability point of view. So this picture shows the basic architecture of the USB IP framework. This slide was taken from the original project website where you see the link to it. Sorry, no HTTPS. And so the project website contains very detailed information about the framework. Also, it has references to the original papers of the authors who designed the framework and their design decisions. It is important to understand here the roles in the framework. So it's a traditional client-server architecture. So server in USB IP terminology is a site which actually exports USB devices, or serves USB devices. So it's a site where you plug in real physical devices and expose them to the IP network. A client, on the other hand, is a site which imports USB devices. So you don't plug anything to the client, you just contact the server, import the device, and the USB IP framework ensures that this device appears to be as it was locally plugged into the client. So particularly in Linux, here are the components which implement the USB IP. So we see client and server there. The components are represented in green. So on the server side, you see a user space daemon, which is called USB IP-D, and it communicates with two kernel modules. They're called USB IP host and USB IP core. On the client side, you have the USB IP client utility in user space, and again, two kernel modules. One is, again, USB IP core, and one is virtual host controller interface. So it's a virtual USB host controller. USB IP core is like a part of a shared code between client and server, so you can think of it as a kernel level library. I'm not sure why it's implemented in a separate module, but that's how it works. And on server side, you can see that this subsystem can talk to a real USB host controller driver. So the basic process of using USB IP is as follows. So imagine you plug in a real physical device to the server. So so the server's real USB host controller enumerates this device and reports to the USB subsystem of the server that a new device is in the system. And Linux will typically try to load the appropriate device driver to manage this device, and that's it. So that's what happens when you plug in a device. So now at some point you want to expose this device of the network. So what you do is you instruct USB IP daemon to send a command to the server's USB subsystem. You command to export the device, and what happens is that USB subsystem just detaches the real device driver and then begins to forward all the data to the USB IP host driver. It means that USB IP host driver becomes the device driver on the server for this particular USB device. So, and at this point, the device is considered exportable. At some point later, a client comes into play, so the client contacts the USB IP server and asks if it can import any device. So what happens then is the USB IP host driver establishes a logical connection to virtual host controller on the client side and begins forwarding all URBs there. And virtual host controller on the client side, in its turn, just injects them to the USB subsystem of the client. So, and it reports that as if a new device was plugged in, and the same happens as on the server side. So Linux USB subsystem will try to load the appropriate device driver, which now begins to manage the remote device on the server. So this is how it typically looks from the shell. We will focus here on the client side of operations because it's of particular interest today. So imagine you already configured a server to export one USB device, and from client what you do, you have the client USB IP utility, and you request a list of exportable devices from a particular server. So you just send the list command and the IP address of the server or the host name. So in this example, we see that the server particularly imports one USB device. You can see its properties, so you can see vendor ID and product ID. You can see the physical device path and some other useful information. What is useful here, you see this when 1/1, it's a bus ID and device ID of the device, so you need it later. So if you want to import this particular device, you execute the client utility again. You just send the attach command. Again, you send the IP address of the server, and you specify which particular device you want to import. So when I originally saw this, my expectation was that the USB IP subsystem conceptually is very similar to a typical VPN. And in VPN case, both sides have some kind of a virtual network interface driver and some user space process attached to it. So on one side, the user space process extracts the low-level network packets from the virtual interface, forwards them to the other side, and the other side just injects them back into the network stack of the for its network stack. Here I got interested that on the client side, on the server side, we have this daemon which runs in the background, but on client side we have only the USB IP client utility, and when you import a device, it immediately exits. So I was wondering, like, how does it work internally? Like, does it fork itself or somehow? And I started to search this user space process which talks to the kernel and injects low-level USB data. But surprisingly, I haven't found any. So the interesting part here that once you import a device, your client utility exits and there is no other processes, additional processes are running in your system. And I was like, what? How can it work then? Then I start digging into the source code, and turns out that the way how it works really is the following. So first, when you send the list command, what it basically does is the client utility opens a TCP connection to the server, sends a request, give me the list of devices, the server just sends a reply, the client displays the reply and closes a TCP connection, and that's it. The interesting part is when you send the request to import the device. So what it does, again, the client sends import request, the server does some plain sanity checks that the device is still plugged in, it's still exportable, and sends a success response to the client. And after that, both sides just pass the socket file descriptor, which represents this TCP connection, directly to the kernel. And after that, the kernel handles all the network communication. So basically, the application level protocol for USB IP is implemented directly in the kernel, and kernel is your service which actually sends and receives data, and which is sounded very, very scary. So it got me interested more, and I started to check the kernel level implementation, which brings us to the vulnerable USB IP code. So to describe it, I will first give a quick introduction to what a USB IP network protocol is. So it's very simple. It's a message-based protocol on top of plain TCP connection. So as most of the protocols, it has a header and section and a data section. So data section contains the URB data, this USB request block data, which is being forwarded. Obviously, it has some length, and like most of the protocols, this length is a field in the header. So if you want to see additional information, here is a link to the protocol description. It's part of official kernel documentation. So the protocol is rather simple. It contains, I think, like 6 messages in total, so it's very easy to read. Which brings us to the client-side receiving code. So if you strip down all unnecessary parts, the receiving code basically boils down to 2 basic operations. One is parse the header, and the second one is receive the rest of the data from the network. If you dive into the parse header function, the interesting part here is that it takes the length from the header and initializes one field in the URB data structure. And URB data structure is an in-kernel representation of USB request block. So this data structure is used by the kernel to pass data between different USB subsystems, device drivers, and the devices themselves. And if you boil down to receive the rest of the data part, what you see is that this value is then used to initialize a local size variable, and then this size variable is used to receive the rest of the data. So unfortunately, there are no checks in between that this size variable, the value of the size variable is actually smaller than the pointer which URB transfer buffer points to. So as a result, we have kernel heap buffer overflow. So basically, it is possible to write arbitrary data to URB transfer buffer, and you can always write past the boundary. But what is this URB transfer buffer? So, as I mentioned, the basic URB structure and the transfer buffer is usually allocated by the kernel or device drivers. So, most of the cases, it's allocated from kernel heap. So, as a result, this is a kernel heap exploit. And another interesting point to know that because how USB protocol is originally designed, so in the slowest level, USB protocol is always host to device. If you do even receive some data from the device, it's still done by request from the host. So this structure is allocated even before we actually send a request to the server in USB IP terminology. So basically, we cannot adjust the buffer size based on the response we receive. And another point that if you try to send malicious packets to USB IP client, from network point of view, even if you have like some network, kind of a network analyzer, the traffic looks totally valid. So, for example, if you send a packet which has a length field 128 bytes and the data attached to it is 128 bytes, it's completely valid packet in terms of USB IP protocol, but you may never know that this packet is destined for USB transfer buffer, which is only 64 bytes long. So this vulnerability received the following number. It's CVE 2016-3955. It's actually received very high CVSS score by US National Security Vulnerability Database, probably because this vulnerability can be exploited directly from the network, and the attacker basically requires no authentication to do it. And although I'm not in favor of giving nicknames to vulnerabilities, practice shows that if a vulnerability has a meaningful nickname, it's easily remembered and it is easier to communicate between security professionals when you say like, oh, do you know about CVE number blah blah blah? I said, what is about? And when you say, hey, you know about Heartbleed? Yes. You know about Beast? Yes. And hopefully now if I say, hey, you know about U-Boat, you will say yes. Unfortunately, usually these vulnerabilities have a logo as well. Unfortunately, I'm a very bad designer, so I didn't do a logo, but if someone wants to contribute a logo, please contact me. I will be very grateful. Okay, so what are the requisites to exploit this vulnerability? So, as I mentioned before, your potential victim has to actually use USB over IP. Most Linux USB IP is enabled in most popular Linux distributions. However, they are compiled as modules, and the official instructions even require you to load these kernel modules before you want to use USB IP. So, if you don't use USB IP, you didn't load the modules, you don't have the vulnerable code, so you're safe. Secondly, your victim has to be client in USB IP terminology, that is the site which actually imports USB devices. I haven't found any issues with the server. So far, it seems the code there proper validates the buffer sizes. So it is only possible to exploit the client. Also, your victim has to import at least one USB device. As you saw from previous diagram, the client becomes vulnerable only when he imports the socket into the Linux kernel. So before that, the client is reasonably safe. So you either have to hijack an existing connection, or you have to somehow trick the client to import a device. And you, as an attacker, you have to either hijack the client's network, although it may be easy because the USB IP uses plain TCP without any encryption or authentication. You still have to get on the client's network and do MITM there, or you can just try to hijack the USB IP server and try to modify its behavior to send malicious responses to the client. Okay, let's do some demo. Just a minute, I will switch the desktop. Okay, here, for demo purposes, we have a US Linux system. For simplicity, I will run client and server on the same system, but you can imagine there are two different systems because you can just use local host network to communicate between each other. And this is like a plain Ubuntu system. So, except that I compiled vanilla kernel, which is still vulnerable to USB over IP, to U-boat attack, because now it has been patched in most distributions. So the right side is a server. So I will not hijack the network for this demo. I will just pretend that I'm controlling the USB IP server. And for this specifically, I wrote a simple Go program which emulates the USB IP server. So it doesn't require any physical devices. It exposes one virtual malicious fake device. So we will start the server here. Okay, and as you can see, as attacker, I don't even require any privileges. I just run it from plain user. As long as I'm compliant to USB IP protocol, I'm okay to trick the client that I'm a totally valid server. So on the client side, first of all, we will check which devices are being imported. So we launch the client utility, and we specify the command list, and we launch the client utility and specify address of the server. Yeah, so I have a logging on the server, so I'm sending a fake device list. And on the client, we see that one device is being exportable. It has a vendor ID and product ID of dead beef, and has a physical path of dangerous UAP demo. Sorry?
Is it possible to increase the font size?
Increase fonts? Yes, sure. I will not increase the server because I will not touch the server now. Is this okay? Okay, so we see that the server actually shows that one device has been exportable. So next thing we should do is, first of all, as I mentioned, we need to load the kernel modules. So USB IP core and the virtual host controller interface. Okay, and now we can try to actually import a device. So the server is configured in a way that once we import this device, when the socket will be passed to the Linux kernel and we will see actual URB traffic, it will send a bigger response than the client expects. So, and we hopefully will crash the system. But it usually crashes, but we'll see like if the demo god is willing to help today. Okay, so now to import the device, we need super user privileges. Again, we say attach. We specify the address of the server. And then we specify which device we want to import. So it's basically this 1/1. If you have more devices, you will have 1/2, 1/3, or 2/1, or whatever. Okay. Okay, it didn't crash, apparently, but we still see some errors on the DMESC. Let's check DMESC output. Oh, I cannot check the DMESC output. So yeah, you see a struct trace in the DMESC output, so apparently we wrote some garbage and the Linux cannot work anymore. Let's try from the server side. Oh, okay, so we crashed the system. It doesn't scale. So it says here that reboot is needed. Oh well. Okay. Okay, so this is like one of the simplest attack possible. But you can do more, because this is easy. You just send some garbage, you try to override some structures with garbage, and most probably the system will crash because it will try to dereference some kind of invalid pointer. What can you do more? As we just saw, you can definitely do denial of service. So I showed you that's easy. You can try to do data injection. So instead of sending some garbage, you can actually try to send some meaningful data and override some pointers. So if you override some data, you will get data injection. If you override some function pointers, you may get code execution. So remember that this is a kernel heap exploit. Code execution is much harder here than if you have a stack. And with case of stack exploits, it's easy. You just override the return address of the function and your code's being executed. With kernel heap exploits, due to the random nature of memory allocators, it's harder, but it's still possible. I will not go in detail how to do that, but you can actually reuse any previous kernel heap vulnerabilities. So some of them have a very detailed explanations how to achieve meaningful result with data injection or code execution. So one particular example is this blog post. So it previously used a vulnerability which lead to kernel heap exploitation, and this blog post has step-by-step with code examples how to gain code execution on the compromised system and elevate your privileges there. However, USB IP vulnerability is actually more flexible for the attacker than most of the other kernel vulnerabilities. So, and to explain this flexibility, I will briefly, on very high level, describe how kernel memory allocator works. So basically, Linux kernel, for its heap memory, reserves some continuous memory regions called slab caches, and each cache has a specific sign attached to it. So it means that if we have a slab cache 32, it means that the whole memory regions is broken into equal chunks of 32 bytes. If you have slab cache 64, you have this memory region broken into 64 bytes, and if you have slab cache 128, you have memory region broken in equally 128 bytes. And I mean, it doesn't have to be power of 2. There are sizes in between. This slide just briefly shows what slab caches are available. So for example, if your kernel code requests some memory, it requests like, let's say 28 bytes and uses kmalloc function for that. So what kernel actually does, it rounds up to the nearest available slab cache, and if there are free chunks there. So technically, if your code would request 28 bytes, it will find the free slot, most probably find the free slot in slab cache 32 and return you this chunk. So your code actually receives a little bit more memory than requested, but it's totally transparent as not its last memory. So if you can exploit that, so what you can override any data in your chunk and any chunk which follows your buffer. So if the other chunks in the slab cache were allocated to a different subsystem, you are basically injecting data to these other subsystems. So what differentiates USB IP vulnerability from other vulnerabilities is that most of the vulnerabilities can exploit only a particular cache size. So for example, if we have an exploit in slab cache 32, we actually, to get some meaningful output, we need to find other objects which are allocated from the same slab cache and then tailor our attack to try to overwrite those specific objects. In USB IP case, interesting part that the attacker has somewhat control which slab cache can exploit, so he can just select whatever structure he wants to exploit and just tailor their attack to a specific slab cache. So this is achievable in the following way. So remember, if an attacker can hijack your USB IP connection, the attacker can actually emulate any USB device on the client system. So the steps would be that if you're an attacker and you want to exploit a particular slab cache of a particular size, you just find any USB driver in the Linux subsystem which allocates transfer buffers from the same slab cache, and thankfully there are a lot of USB drivers in the Linux kernel, so you can select any one. When you hijack the connection, you emulate this USB device, so the target, so most modern Linux distribution will load this device driver automatically when we see that the device appeared in the system, and when the driver has been loaded, it will start allocating object in your desired slab cache, and then you perform your attack. Okay. Still interested in using USB over IP? Okay, if you still do, then here are some tips which will help you harden the USB IP setups. So first, if you're still thinking of using it, just please reconsider. Maybe if you have a device and you want to share it between different systems and the device is cheap, just buy another one, so it's probably safer. Because still, even though your system may be already patched and protected from the vulnerability, the attacker can still emulate any USB device on the client system, and this is still pretty scary. So attacker can just emulate a screen, for example, and get all your screenshots, or a mouse and try to disrupt your work or whatever. If you're still keen on using it, definitely patch your system, and this advice applies to everything actually. If you're using Linux, you should patch quickly and patch often. Most distributions provide you with security updates and security advisories, and kernel is a very important part of that because it's very high privileged, and different vulnerabilities are being discovered every day. So definitely stay on top of security patches. protect your traffic. Unfortunately, original USB IP doesn't have any built-in security mechanism apart from a very simple access control, which can limit the connection to USB IP server from specific IP addresses. But in today's world, what's an IP address? So it can be easily spoofed. So as you saw, the attacker can attack a client even if the system is patched, if the attacker can hijack a TCP connection. So if you somehow wrap the connection in TLS or IPsec, for example, it even doesn't have to be encrypted, because encryption is important, but at least authenticated, you prevent the attacker from hijacking the traffic. And do this even in your internal network, because even if you're home and you have just a plain home Wi-Fi, you know the state of the modern IoT world and how secure are IoT devices, so you may never expect who is sitting on your home network and doing what. And definitely ensure your USB IP server is sufficiently protected and proper access control mechanisms are in place, because if the attacker will not be able to hijack your network, that the next step would be probably to hijack your USB IP server and take control of it and try to spoof the responses it sends. Okay, here are additional resources if you want to read more. So this is a link. The first one is a link to an original blog post I wrote about this vulnerability. It has a very detailed source listing and shows where the vulnerability particularly is and all the code flow which leads to it. Second, if you want to play with my malicious USB IP server, you can download it from GitHub. And it's actually a Go program. Originally, as a proof of concept, I wrote a C server. It was very ugly, so I decided to rewrite it in Go, and now it's a very plain, simple Go program, which is Go gettable, Go buildable, using all your standard Go tools. So it's very easy to start using it. Then the link to the original CVE database. It's useful because it has many links attached to it of different kernel distributions and forums which discuss the vulnerability and provide more details of the potential impact and more constraints. And the last one is the National Vulnerability Database, which provides the CVSS score. It has a detailed breakdown why this vulnerability received a high CVSS score, although it's not widely used. Okay, so Black Hat sound bites. First of all, never sacrifice security for performance. So I was puzzled why the authors of the USB IP framework implemented the application network protocol directly in the kernel. It sounds very dangerous. I read through their articles and I was seeking for evidence that it was impossible to do the other way, but unfortunately I haven't found any. What I found is one sentence that says, hey, but by the way, we want to avoid this extra buffer copy between kernel and user space, so we just put everything in the kernel. So don't do that. If this performance doesn't hit you, so leave it. Leave this extra buffer overflow, extra buffer copy for the sake of security. I know another big company actually does similar. It implements application level protocol directly in kernel. I will not name the company, but last time I checked, they still had this HTTP implementation in Windows 7. So, secondly, always validate your input. So if you're designing a system which communicates to other systems, even if it's a library, especially if it communicates over the network, or if you communicate between kernel and user space, always expect that your input might be malicious, hijacked, and try to do as much sanity checks as possible on the input you receive. And lastly, consider release privilege principle. So this is what is not done in the USB IP framework. So you should break your code into modules. It's understandable that such frameworks such as USB IP, some parts of it require very high privileges to inject low-level USB data into the kernel. So if you break your code into modules properly and make the modules which require high privileges as small as possible, they will be easy to review, easy to audit, and you will dramatically reduce the attack surface for your code. So, and everything else should be as least privileged as possible. That's it. Any questions? Yes? So the question was, what's the probability of you're able to crash the target system? Actually very high. During my demo development, I crashed the system 9 of 10 times. I did specifically make a patch which dumps the memory if the system did not crash. That's why I tried to run dmasks and show you that I definitely did the buffer overflow, but most of the time it crashes. It also depends on how much of the buffer you will override. So by default, the server I implemented overrides the cache by 512 bytes, which is pretty large, so there is a big probability I will hit some kind of a control structure. If you override the buffer, for example, for 1 byte or for 2 bytes, the probability is much lower, so you can actually use it system. But if you do want to crash the system, it's very definitely you are going to crash. So even if you didn't crash the system for the first time, the next time it crashes, so within 2 attempts. Yes, please. So the story of it is actually very simple. As I mentioned, I'm not an InfoSec person. I don't specifically look for vulnerabilities. What I wanted to do, I had like my own project. I wanted to design a framework which emulates USB devices and software. So I started thinking, okay, what I need to do? So first of all, I need a virtual USB host controller driver, and obviously I didn't want to write it from scratch, and I started searching around what options are available and stumbled upon USB IP technology. So my original intent was not actually to expose devices over the network, but just reuse the same driver to emulate USB devices in software locally. And the reason I started digging into the source code because I wanted to find out what the interface of communicating with this driver. And while doing that, I figured out that indeed it does network communications directly from the kernel. And when I started looking deeply, I just saw this vulnerability. So I may say it was just found by accident. Yes? So the question was, are there any popular projects with using this software? No, unfortunately. I even was very surprised that this framework is part of the vanilla kernel source tree, because I never heard about it and I didn't see any use cases. So that's why I assume it's highly unpopular, or just people do not know about it as well. Thank you.